In this lesson, we'll look at proofs by strong induction. You'll notice the comparison to the regular induction we did a couple of videos ago, but there's one big change. First off, you've got the same statements getting you going. These are all of our base cases. But then what has changed is the last statement. This statement's a little bit more complicated. What we have is for all k greater than or equal to b, which hasn't changed. But our assumption has. We no longer assume just p of k. We assume that for all I between a and that sum k, p of I is true. But if we have all of the values for p of a through p of k, then we can show p of k plus 1 is true. If we have this claim, then we can also say that for all n greater than or equal to a, p of n is true. Let's look at how to prove by strong induction. Again, your base case is exactly the same. However, in some of these strong induction proofs, there's a little more of a chance that you're going to need more than one base case. You start off by just proving some early numbers into the statement. But for the inductive case, what changes is that you'll take some k as usual, but instead of assuming that just p of k is true, you assume that p of I is true for all the values from a up to k. In other words, instead of just getting to assume p of k, you can assume p of k and everything that came before it. Then you prove that p of k plus 1 is true. We'll only do one example of this concept, but this concept can be used to prove a lot of different interesting theorems. One such is the Fundamental Theorem of Arithmetic, which says that every number has a unique prime factorization. Strong induction can also be used to prove a number of statements that look like this one. Now this one looks a little bit random, but let me tell you a little context. If you think of a football game, and you look at 3 points for a field goal, or 7 points for a touchdown, not assuming really anything else going on, then the total score that the team would have is 3 times the number of field goals plus 7 times the number of touchdowns. Just using these constraints, it's possible to attain any score in the game of at least 12. Yes, there would be some game time constraints and that sort of thing, but looking at theory itself, any score of at least 12 is possible. There's plenty of other examples that can come out of this as well. Basically, anytime you're trying to build a number from smaller numbers, such as piling 2 different sizes of bricks together, you can figure out that a certain total is possible after a certain point, and it can keep going one at a time that all of those numbers are possible, theoretically forever. Let's do this problem. We'll start off with our base case, just like standard induction. Consider n equals 12, 13, and 14. I'm picking 3 base cases for reasons that will become clear as we go, but I will tell you the 3 is based on the smaller number here, being a 3. Now let's see if we can find a way to do it. Just by plugging in values for x and y, we need to somehow get 12, 13, and 14. You might find it interesting to try these yourself. Here's the first one. For n equals 12, use x equals 4 and y equals 0. For n equals 13, use x equals 2 and y equals 1. For n equals 14, use x equals 0 and y equals 2. How many of these did you get on your own? Now let's move into the inductive case. The wording here needs to be a little bit more careful than what we did with regular induction. Assume, for some k greater than or equal to 14, again k picks up where you left off, just like it did for regular induction. But now I need to assume that the statement holds for all values of k up to 14, and starting at our 12 starting point. That there are numbers x and y in the natural numbers such that 3x plus 7y equals I. Now I is going to represent any number between 12 and k. For some I in the natural numbers, such that 12 is less than or equal to I is less than or equal to k. In other words, I can find these numbers x and y for any value of I between my starting point of 12 and wherever k currently is. Now I want to show this for k plus 1. To show it for k plus 1, I'm actually going to go backwards 3. Again, my inspiration is looking at this 3 right here. I'm thinking if I can go 3 backwards and get an answer, then I could add one more value of x to get another 3 and get my final answer. You'll see how this works as we go forward. But for right now, I'm going to consider k plus 1 minus 3, which is k minus 2. Then by the inductive hypothesis, there exists an x and y in the natural numbers, such that 3x plus 7y equals k minus 2. Now one very important point. Why can I use the inductive hypothesis? Remember, the inductive hypothesis holds for any value of I, as long as I is between 12 and k. It might be important to notice that k minus 2 is at least 12, because k was at least 14. This is why I did a few base cases, because I wanted to make sure that if I took k minus 2, then I would still have a valid use of the inductive hypothesis. Now let's finish the proof. Thus, 3 times x plus 1 plus 7y. Again, like I said, I'm going to use another value for x and just pick a larger one. Well, this is equal to 3x plus 7y plus 3 by distributing my 3, but 3x plus 7y was equal to k minus 2, and then I've still got the plus 3. That gives me k plus 1. Since x plus 1 and y are natural numbers, these numbers satisfy the statement. So my inductive case is done. Let's just write a summary statement. Thus, by strong induction, the statement holds for all n greater than or equal to 12, and that is the end of our proof. We'll only use this one example for this particular video, but remember that strong induction can be used to prove very interesting claims. Let's summarize. How do you prove a statement using strong induction? What do you think? Again, we break this up into two cases. First, show at least one base case is true by substituting in values. Then assume that the statement is true for all values up to some k, and prove that the statement is true for k plus 1.